All right, so today we're going to be taking a deep dive into something pretty incredible, the chemistry of planets.
Wow, yeah.
It's really amazing to think that these celestial bodies are not just like, rocks and gas out there.
Right.
There's so much more to it.
Yeah.
And you've actually sent over some really fascinating facts about the different elements that make up these planets.
Yeah.
From, the rocky planets that we're familiar with to gas giants and even ice giants.
hmm
It's incredible. Like, who knew there was so much variety in space?
It really is mind-boggling when you start to, wrap your head around it.
Yeah.
As we often picture planets as these kind of uniform spheres, right?
Right? Yeah.
But when you look at their chemical makeups, you realize they're incredibly diverse. And that's really where things get interesting.
Yeah.
Because these elements aren't just sitting there passively, they're building blocks of entire worlds.
Wow.
And they shape everything from a planet's appearance to its potential for, even harboring life.
Okay, so we're not just talking about like a boring periodic table here.
Right.
This is about understanding, the ingredients that make each planet unique.
Exactly. It's like having a cosmic recipe book.
Okay.
You've got your base elements, the ones that were forged in the hearts of stars and, from the Big Bang.
Right.
But how those elements combine, how they react,
Yeah.
and how they settle under different gravitational forces, temperatures, pressures, that's what dictates the final product.
Okay, so kind of like baking a cake.
Yeah,
You can have the same basic ingredients, but,
exactly.
the proportions and the oven temperatures
Yeah.
may make all the difference.
It's a great analogy.
Okay.
Because just like a cake can be light and fluffy or dense and rich, planets can be rocky, gaseous, or icy,
Right?
depending on their elemental compositions.
Okay, I'm ready to dig into these cosmic recipes. Where do we start?
Let's start with what's familiar. Rocky planets.
Okay.
You're standing on one right now.
Yeah.
And it's not the only one in our solar system.
Besides Earth, are there other rocky planets like hanging around?
Absolutely. Mercury, Venus, and Mars are all part of the Rocky Planet Club.
Gotcha.
They're composed primarily of silicates and metal oxides.
Okay, silicates and metal oxides. Those are words I haven't heard since high school chemistry.
Right.
Remind me what those are again?
Well, think about it this way. Silicates are the most common minerals on Earth.
Okay.
They make up a large portion of the Earth's crust and mantle.
Huh.
Everything from the granite in mountains to the sand on beaches is largely composed of silicates.
Wow, so silicates are kind of a big deal.
Kind of, yeah.
And what about metal oxides?
Metal oxides are exactly what they sound like. They're metals that have reacted with oxygen.
Uh-huh.
A very familiar metal oxide is iron oxide, more commonly known as rust.
Wait, rust?
Yes.
Like on cars?
Exactly.
Wow.
And that's actually what gives Mars its distinctive red color.
Oh, wow.
It's essentially a giant rusty planet.
That's incredible. I always knew Mars was called the Red Planet, but I never, put two and two together.
Right.
So all those, rusty landscapes we see in pictures,
Yeah.
that's literally billions of years of iron oxidate.
Precisely. It's a dramatic example of how planetary chemistry shapes a planet's appearance and tells a story about its history.
That's so cool.
Yeah.
So we've got these 4 rocky planets in our solar system,
Right.
all built primarily from silicates and metal oxides.
Mm-hmm.
What about the other planets?
Yeah.
What are they made of, if not rocks?
That's where we venture into the realm of giants, the gas giants to be precise. That's right. No solid ground on these planets, just massive swirling atmospheres.
Okay, so no landing on Jupiter for a picnic. Got it. But what makes up these giant atmospheres then?
It's pretty simple, actually. Hydrogen and helium, the 2 lightest elements in the universe. In
Okay.
fact, they're the very first elements to form after the Big Bang.
Oh, wow. So these gas giants are like giant time capsules, holding on to the earliest building blocks of the universe.
In a way, yes, it's pretty amazing to think about.
It is.
That these planets are mostly made up of elements that have been around since the dawn of time.
Yeah, so if hydrogen and helium are gases here on Earth, what makes them so different on gas giants like Jupiter and Saturn?
That's where gravity comes into play.
Okay.
The immense size and mass of these planets
Yeah.
create these incredible gravitational forces, unlike anything we experience here on Earth.
Uh-huh.
Just imagine the pressure at the bottom of the ocean.
Okay.
Now multiply that by thousands, and that's the kind of pressure we're talking about on a gas giant.
Wow, that's got to do something pretty crazy to those elements.
It does, deep within Jupiter. For example, scientists believe that hydrogen is squeezed so tightly by gravity
Yeah.
that it actually transforms into a metallic state.
Metallic hydrogen. That sounds like something out of a science fiction movie. What does that even mean?
Essentially, it means that hydrogen starts behaving like a liquid metal.
Huh.
It can conduct electricity, and it's thought to be the reason behind Jupiter's incredibly powerful magnetic field,
Wow.
which is thousands of times stronger than Earth's.
That's wild. So extreme connections can completely change the properties of even the simplest elements?
Uh-huh.
So we've got the rocky planets with their silicates and metal oxides,
Right.
and the gas giants with their hydrogen and helium, some of which is behaving like metal.
Yeah.
But what about those ice giants? Where do they fit into all of this?
The ice giants, Uranus and Neptune.
Okay.
They're kind of like the cool, mysterious cousins of the gas giants.
Okay.
They've got these thick atmospheres dominated by hydrogen and helium, just like Jupiter and Saturn.
Yeah.
But what sets them apart is the presence of, you guessed it, ice.
Okay, but when we're talking about ice in space, are we talking about, like, the same kind of ice we use to chill our drinks?
Not quite when astronomers talk about ice.
Yeah.
They're referring to any compound that would be a gas at Earth's temperature,
Yeah.
but freezes solid in the much colder temperatures of the outer solar system. So in addition to water ice, we're also talking about frozen methane and ammonia.
Methane and ammonia. So those ice giants are basically giant frozen stink bombs hurtling through space.
Well, you could say that.
Okay.
But in all seriousness, these ices play a big role in shaping the appearance and characteristics of ice giants.
Okay.
For instance, Neptune's deep blue color is actually due to the methane in its atmosphere. It absorbs red light and reflects blue light.
Wow, that's incredible. It's like a cosmic color palette with different elements creating these stunning visual effects.
It really is.
So we've covered rocky planets, gas giants, and ice giants. But there's one more thing I'm really curious about.
Yeah.
The connection between planetary chemistry and the search for life beyond Earth.
Now, that's a fascinating topic, and it's where things get really exciting in the field of astrobiology.
Yeah.
Scientists are constantly searching for what are called biosignatures.
Biosignatures, those are like chemical fingerprints that might indicate the presence of life, right?
Exactly. Imagine you're a detective at a crime scene.
Okay.
You're not looking for the culprit directly. You're looking for clues that they left behind.
Right.
Fingerprints, footprints, DNA, things like that.
Gotcha.
Biosignatures are kind of like the cosmic equivalent of those clues.
So what kind of chemical clues would scientists be looking for on other planets?
Well, some of the most promising ones include the presence of things like water, methane, oxygen, and even more complex organic molecules.
Okay.
These molecules are often associated with biological processes here on Earth.
Right.
So finding them in the atmosphere of another planet could be a strong hint that life might exist there.
So if we find a planet with a similar chemical composition to Earth, one that's rich in water, methane, maybe even oxygen, does that automatically mean there's life?
Not necessarily. It's important to remember that these molecules can also be produced through non-biological processes. That's why scientists have to be very careful when interpreting these findings
Yeah.
and look for multiple lines of evidence to support the possibility of life.
So it's like putting together a puzzle.
Uh-huh.
One piece might not tell you much, but when you start to fit multiple pieces together, you get a clearer picture.
Precisely. And the more pieces we find,
Yeah.
the better we'll understand the conditions necessary for life to emerge and the likelihood of finding it elsewhere in the universe.
This is also fascinating. It's like we're peeling back the layers of the universe one element at a time.
Yeah.
But how do scientists actually go about detecting these biosignatures on planets that are light years away?
It is a challenge, but
Yeah.
scientists are tackling it with some incredible ingenuity. One of their most powerful tools is spectroscopy.
Spectroscopy, that rings a bell from like high school science class, but I'm a bit rusty on how that works.
Yeah.
How does that help us analyze planets from so far away?
Well, it's all about light. Spectroscopy allows us to break down the light coming from a distant planet,
Okay.
kind of like a prism splitting sunlight into a rainbow.
Right.
But instead of just pretty colors, we get a detailed spectrum.
Uh-huh.
And the spectrum is like a unique fingerprint of the elements and molecules present in the planet's atmosphere.
So by analyzing the spectrum, scientists can figure out what the atmosphere of a planet that's like light years away is made of.
Exactly. Each element and molecule absorbs and emits light at very specific wavelengths.
Okay.
It's kind of like they each have their own signature tune.
Hmm.
So by analyzing the light that passes through a planet's atmosphere,
Yeah.
we can detect those tunes and identify the players, so to speak.
So it's like we're listening to a planet's breath and figuring out its chemical makeup.
Yeah, you could say that.
That's pretty cool. But I imagine this takes some seriously powerful telescopes, right?
Oh yeah, we're talking about some of the most sophisticated telescopes on Earth and in space.
Okay.
They're equipped with spectrographs,
Uh-huh.
which are these instruments that act like super-sensitive prisms,
Okay.
splitting the light into its component wavelengths
Yeah.
and creating those spectral fingerprints that we talked about.
And the James Webb Space Telescope that's playing a big role in all this too, right?
Absolutely. The James Webb Space Telescope is a game changer for astrobiology.
Yeah.
It's got such powerful instruments that
Yeah.
it allows us to study the atmospheres of exoplanets.
Okay.
These are planets orbiting other stars with incredible detail.
Wow.
We're now able to detect much fainter signals and analyze the chemical compositions of planets that were previously beyond our reach.
It's like we suddenly have a much clearer view of these distant worlds.
Right.
But even if we find all the right ingredients for life,
Uh-huh.
the water, the methane, maybe even oxygen, how can we be sure it's actually life and not just some weird geological process mimicking those signatures?
That is the million-dollar question,
Yeah.
and it's something that scientists are always thinking about and grappling with.
Right.
One approach is to look for combinations of biosignatures that would be very difficult to explain through any kind of non-biological process.
Gotcha.
For example, finding both methane and oxygen together in a planet's atmosphere
Yeah.
would be a pretty strong indication of some sort of biological activity going on.
Okay.
Because those two gases tend to react with each other and destroy each other
Uh-huh.
unless something is constantly replenishing them.
So it's about looking for those unlikely pairings, those chemical imbalances that scream life.
Exactly. It's like detective work, piecing together the clues to solve a mystery.
It really is. And the more clues we find, the stronger that case for life becomes.
Yeah.
This is a pretty thrilling time to be following astrobiology, because it seems like we're making discoveries all the time,
It really is.
like pushing the boundaries of what we know about the potential for life beyond Earth.
Yeah. Every day, it seems like.
It really makes you wonder what's out there.
Yeah.
If we do find compelling evidence of life on another planet, what do you think that will mean for humanity?
That's a big question, a really profound question, and one that we can only really speculate about.
Right?
But I think it would have a transformative impact on our understanding of our place in the universe.
Yeah.
It would force us to reconsider the uniqueness of life as we know it,
Right.
and potentially open up entirely new fields of study and new philosophies.
It's almost too much to wrap your head around,
I know, it's exciting.
but it's also incredibly exciting to think about the possibilities.
Absolutely. And that's the beauty of science. It constantly challenges our assumptions and expands our horizons.
Well said. So we've explored the amazing diversity of elements that make up our celestial neighbors, from the rocky planets with their familiar silicates and metal oxides,
Yeah.
to the gas giants with their swirling hydrogen and helium, some even in a metallic state.
It's crazy.
And then there are the ice giants cloaked in their frozen methane and ammonia.
Right.
And through all of this, we've glimpsed the possibility that we might not be alone in the universe.
Yeah.
As we continue to develop new technologies and peer deeper into the cosmos,
Yeah.
who knows what incredible discoveries await us?
Who knows?
Perhaps one day we'll find that life in all its diverse forms is not the exception, but the rule sprinkled throughout the vastness of space. Each world, a unique cocktail of elements, each a story waiting to be told.